Okay, great. So we got 3 more weeks of class. Okay, so this week we'll finish up chapter 6. Then we'll have a test next week. Then we have 2 weeks when we'll be looking at chapter 8. That'll be our last chapter. In that last week, we don't have a test, but you will present your projects. And then in the exam time, we will have a test for this class. Half of it will be on chapter 8. It will just be a normal test that you used to, but it'll be on what we're doing in the last 2 weeks. And then the other half will be a comprehensive exam of short questions. Okay, the project, so you should start having a look at the project because quite often there's a few things you have to kind of understand to get started with the project. And so you should sort of get that sorted out fairly quickly. It's you're working with someone, so you should look at the project, figure out what you've got to do, divide up the tasks, and then, at some point meet and decide what's going to happen, right? So for the final presentation, usually what you do, you make like a little PowerPoint where you present the problem and use your solution, give the solution. So quite often you might have to do an Excel file to help, because a lot of the time there's lots and lots and lots of calculations to do, and so the Excel file is good for that. So if you need some help with that, you could definitely come and see me. So I really suggest that you meet with your teammate and then kind of make an appointment with me so that we can all meet at a particular time and have a good chat about what needs to be done. Eric?
So for the last comprehensive test, is it weighted like one of our normal tests, or is
Yes.
it weight up?
Yeah, so I believe what it is like there's 2 tests though on the last day. Okay, so they're all the same weight. So the test on chapter 8 is just like the test that's coming up on chapter 6. So that's one unit of test, and then there's a comprehensive, which is another unit of test. Okay, and that for that comprehensive bit test, I kind of look at it, and that kind of helps me guide what's going to happen in close situations, kind of thing. Okay, so that's kind of like the test I use to say, well, someone did badly here, but they did well in the comprehensive, so I might give some points, extra points to make up, whatever, to help me make those life and death decisions. Okay, and so that's kind of like a plan. Okay, so so we're coming towards the end. So as I said, besides the homeworks, there's the two chapter tests plus the comprehensive test. So that's like 3 tests plus the project. The project consists of a write-up and a presentation. So each of those is kind of like worth a homework. But so usually what happens with the write-up, I grade more on kind of correctness, like whether you did the math right. And for the presentation, I kind of say, look, how well did you present the problems? Like how good was your performance? But I know you guys, a lot of you people are in business, and you guys seem to do good presentations. So that's always comes out. Okay, so let's talk about, so we're continuing with chapter 6 with integration. And so really, we now know how to do a lot. In particular, we know how to find an integral. And so remember, there were two types of integral. There was the indefinite integral and the definite integral. So the definite integral looks like this. And it's the signed area underneath the curve fx between a and b. And then there's the indefinite integral, which just says take the antiderivative of this function. Okay. Now, notice we're using the same symbol, and the reason why we can use the same symbol is they're the same thing, basically. So the only difference between them is that this is a particular thing, so it's kind of like numbers are plugged in. This is kind of like a potential thing, waiting for something to be plugged in. And so it's the fundamental theorem of calculus that tells us the link between the two things, right? So that if you've got a continuous function, little f, and its antiderivative big F, i.e. the derivative of big F is little f, then this definite integral, the way that you evaluate it, is you take an antiderivative and you take the difference between capital big F of B and big F of A. So this is both the total change and the area underneath the graph. So just like the derivative was both an algebraic thing and a geometric thing, it was both the rate of change and the slope. The integral is also two things, an algebraic thing, the total change, and a geometric thing, the area underneath the curve. Okay, so let's do like a really simple example. Okay, so one way we can do this is geometric way. We can just look at the area underneath the graph of 2x. So this is 0, 1, 2, 3. At 1, it's equal to 2. At 2, it's equal to 4. And at 6, and 3. Okay. So there's 2x there. So we just do the area underneath the curve. We see that it's made up of two things, a rectangle, the square, it's a 2 by 2 square. And it's a 2 by 4 triangle. Well, it's a triangle, so we have to do a half base times height. So this is 4, this is 4. So it's 8 just by looking at it in an area. Second way we can do it, we can do a formula way, right? We can take an antiderivative of 2x. Okay, so when we take its derivative, gives us 2x. Well, that's x squared, right? Derivative of x squared is 2x. So the other way to do this is we can take x squared, and this is just notation which says kind of evaluate it between 3 and 1. So that equals 3 squared minus 1 squared is 8. Agora, a miracle. It's the same thing. And it's always going to be the same thing. Okay? So that means, so before, the only way you had to do a definite integral was to figure out the area. And you can either do that by some kind of geometry like this, or by doing an Excel file and adding up lots and lots of of rectangles and taking a limit. Now we can do formulas. If we know the antiderivative, then we can figure it out.
So on one where you don't really need to do it, you can't do it if there's one where it's not.
So if you don't know the antiderivative, then you have to use an Excel file or somehow to do the geometry. Put circles, triangles, and rectangles there. Yes. And you're right to be a little bit pessimistic because, as I said before, antiderivatives are not as straightforward as derivatives, right? Because for derivatives, you've got a rule that'll do it. A product or quotient or whatever, you can take its derivative. Taking an antiderivative, you've got to say, well, when I take its derivative, will I do that? There's not as much hard and fast rules. You have to kind of sometimes be kind of tricky to do it. And if in some calculus classes, we spend weeks on studying various techniques. We're not going to do that in this class. We're going to be more interested in some of the applications. So for the rest of this week, we're going to have a look at two economic applications. One is consumer surplus and producer surplus. People heard of that before? Okay. So if you know that it's an integral. It's because it's an area underneath the curve, right? So that's the thing. And then the other thing is income streams, which is like, you have an annuity, for example, which gives you a stream of income over time. You can kind of think of that as an integral, right? Because you're getting money all the time. So it's being added up over. But then at the same time, you have to worry about the interest rate. So we know that money in the future is not the same as money now. And so you have to take into account what that money is worth in that time. And so it turns out that you have to do an integral. It's in a very natural way. So that's what we're going to do the rest of the week. Okay, so let's kind of just do a few more examples. So one nice thing is, since we're not going to go into all those complicated things, I'm not really going to give you something which you need to do a really tricky antiderivative to do. Okay. So let's do a couple of examples. Okay, so this was kind of like the typical kind of problem where before you would, but using the method of antiderivatives, it's pretty straightforward. So you've got to think, well, what function, when I take its derivative, is going to give me 3x squared? X cubed, right? And so remember, there's kind of like a power rule for antiderivatives. The power rule for derivatives is bring down the power and then subtract 1 from the power. Okay, so that means the power rule for antiderivatives is you add 1 to the power, so x squared becomes x cubed, and then you divide by that new power. So we divide through by 3. And so you can always double check by taking the derivative afterwards, right? And since you're much better at taking derivatives than antiderivatives, it's always going to give you, that's always going to be a help. Okay, so this is x cubed, and then we just do this kind of notation, which is kind of like an evaluation notation. And so that means this is equal to 4 cubed minus 1 cubed. 64. In the same answer you would have gotten if you'd done an Excel. Okay, so that's the main trick you have to get in your brain is just undoing the antiderivative. Let's do a sine. Okay, this is vaguely interesting, right? Because what is this asking? This is asking for what's the area underneath one arch of the sine curve. Okay. Again, we've got to think. So we know the derivative of sine is cosine, and the derivative of cosine is minus sine. So that means the antiderivative of sine is minus cosine. As I warned you before, that's one that kind of always, people always kind of get it wrong, just get mixed up. Again, we do our evaluation thing. So this is equal to minus cosine of pi plus cosine of 0. Cosine of pi is minus 1. It's 2. It's pretty interesting. The area under there is 2. Okay. So quite often, when you do problems like if this was like an indefinite, if this was an indefinite integral problem, right, the answer would have been minus cosine x plus c. For a starter, we don't need to worry about the plus c when we evaluate, right? Because what are we doing? We're doing this minus this. So if there was a plus c, we'd have plus c and then minus c. So to do this, we only need an antiderivative. We don't need the antiderivative. The second thing is, this is typically where people screw up. Like in the exam, they forget to do the minus. But if you're doing a definite integral, you know what the answer is. This has got to be a positive answer, right? It's got to be an answer. Like this goes from 0 to pi. This is pi to 1. Okay. So this answer has got to be at least, you know, pi on 2, for example. There's a triangle of area pi on 2 that we can put in there. Right, so you kind of expect an answer between 1.5 and 2.5, just from what you understand it to be. So if you get minus 2 as the answer, you think, oh, that's because I forgot that. So when it's a definite integral, you've got chances to recover if you make a mistake. So always when you do a definite integral, you should look and say, does this answer make sense? Because you know that it's an area. Okay? So let's do an exponential one. Okay. Exponentials sometimes get people kind of mixed up a little bit because it's an exponential, not a power, right? So people like to sometimes make the mistake of treating an exponential like a power. Remember, the derivative of an exponential is an exponential. The antiderivative of an exponential is an exponential. So the first thing you should write down is e to the 3t, because that does not change. Okay, so the power of an exponential doesn't change, unlike the power in a power function. Next, what's the right coefficient here? Well, remember, when we take an integral, we divide instead of multiply. So if we had e to the 3t and took its derivative, that would give us 3e to the 3t. That means we do the opposite thing when we take its antiderivative. So that means we divide by 3. So we take the 15 and we divide that by 3. Again, we do 1, 0. So that equals 5e to the 3 minus 5e to the 0. 5e to the 3 minus 5. And that's enough. So just writing e to the 0 as 1 is enough simplification. You don't have to then go and put this into a calculator. This is a perfectly good answer. A couple more. Another important thing to remember is kind of just like the linearity of everything. So if I have, like, I don't know, 3x squared plus 4x plus 2x, to take the antiderivative, I just take the antiderivative of each thing. So the antiderivative of 3x squared, x cubed. The antiderivative of 4x, (2x squared). The antiderivative of 2, 2x. Exactly. A lot of you are trying to say 0. No, it's not. That's the derivative. Okay. Again, we do the evaluation thing. So in a test, remember to do this step, right? Because typically what I'm going to do is I'm going to give points for this and then points for that. So this is like always a key step. And so then you have 2 cubed plus 2 times 2 squared plus 2 times 2 minus 1 plus 2 plus 2. 8 plus 8 is 16 plus 4 is 20 minus 5 is 15. Be careful with the brackets. I had everything positive, but if this had been kind of like a negative, say, another place where people commonly mix up is like you have a minus and then there's side of the bracket, you got a minus there. So this minus minus should be a plus. So making a mistake with signs is a very common error that I see on, particularly on tests when you're like working away under pressure. So, you know, use your brackets. Don't try and do too much at once. You know, like show working on the page. That will help you get the right answer. And then finally,